Hello and welcome to Chapter 5, all about data transformations for further mathematics. This entire topic is all about what if you could adjust the scales on a set of axes in order to make a series of dots on a scatter plot that look like a curve, if I can use that kind of look like this, and if I can go, it might help if I, we want curves that look like that. If we can straighten them out. Why do we want to do it? Well, what we established earlier in the linear regression topic was that the straighter that all of the dots are, or the closer they are to a line, the stronger the correlation is between the explanatory variable and the response variable. And what's the point of all of that? Well, the point of all of that is that the stronger the correlation, the more useful that line is to predict other results that we don't see in the scatter plot. The stronger or the more reliable that correlation, the better we can predict for future events or even earlier events. And today is all about looking at sets of data and how we can go about doing that. First and foremost, what I would suggest we do is have a look back at some chapter 1 knowledge here, where we were looking at the log scale. In case you've forgotten, the idea of the log scale is to be able to take a series of data values that are a mixture of sizes and being able to put them on a number line such that there is a much smaller gap in between. This is rather useful, especially when we've got a huge discrepancy between values. Just as an example, what we've got here. So as an example, we've got the numbers, and I'll get my little highlighter here. 1, 10, 100, 1,000, and 10,000. So there's a very, very large gap between some of them. After all, if I was to plot just even the number 10,000 on here, and then I was to plot the number 1,000, there's a huge gap there. And then trying to go and put 1, 10, and 100 such that it was accurately on this scale is very difficult. It'd be about here, and then about here, and then about here. And even then, I've probably not done it terribly accurately. So in order to improve my accuracy, what I need to do is to create a new scale to be able to put all of these such that we've got some better perspective. Now, back in, say, primary school, for instance, when we were doing bar charts about, what was your favorite colored, I was about to say favorite colored pizza? Yeah, sure, why not? Your favorite colored pizza. I like red. What you would do is you would go and set up all the different columns, and instead of writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you might go 2, 4, 6, 8, or you might do 3, 6, 9, 12, and that way you don't have like one bar being tiny, one bar being huge, and all of that kind of business. So this is that similar principle, but I suppose slightly more mathsy, if you like, for a non-word. So basically what a logarithm does, in a very simplified way, is it goes and summarizes how many digits you might have. Just as an example here, and I know there's going to be some maths people watching this going, no, it doesn't, logarithms don't do that. But from a very simplified point of view, it kind of does. If I did the log 10 of 10,000, that is actually equal to 4. Now, how did I know that? And I'm not the cleverest person or whatever. Well, it's because I used my CAS. And what I'm going to do is I'm going to go and use it to type in said answers. So log 10, 10,000, and I get 4. For 1,000, so I can plot that big point there. For 1,000, what I can do here, log 10, 1,000. So when I put that in, I just have to delete 1. That gets me an answer of, come on, 3. I can plot that there. If you've got a number somewhere between 1,000 and 10,000, then it will be a decimal number, something like 3 point something. So for instance, if I did, let's go 5,000, so somewhere in between 1,000 and 10,000, what I'll end up having is I'll get 3,000 or 3.69897, etc., 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 which you'll notice is a little bit more than halfway, but we'll cross that bridge when we get to it. The idea is that it's somewhere in between, and this is when those mathematicians were saying, well, it's not really a count of zero. Well, this is what they're arguing about. The important thing is that you know that this is the scale. Anywho, and then for 100, so we'll put 100 in, so you can probably predict that it's going to be a 2, so we'll put in green. So log 10 of 100 is equal to 2. And then we can put a log 10 of 10 is 1. It's equal to 1. And then you can possibly guess from this pattern that I've prepared here that the log 10 of 1 is equal to 0, because there's no zeros. So when I make my little graph, as you can see, or when I've done my number line, I can actually see all the values, and I haven't got a huge radical big space, and I can be a little bit more accurate. Now this, in the grand scheme of things, we use this in data to be able to stop getting clumps of dots at one end and maybe a few gaps in the other. We go and adjust the scales in order to try to get all the dots, to, instead of being in a big clump, to actually sort of straighten up together and to form a straight line. Broadly speaking, we use these three transformations here. There's squared transformations, logarithmic transformations, and reciprocal transformations. A squared transformation just means that I'm multiplying that variable's number by itself. Logarithmic, well, you've seen an example of a logarithmic transformation. It's just when I'm doing the log 10 of certain numbers. Reciprocal is just a fancy word for saying 1 over some particular value here. So 1 over x, or in this case 1 over y. I'm either dividing all the explanatory variables, the x, 1 over all of them, or I'm doing 1 over all the response variables, that being the y. Broadly speaking, we've got sort of four main shapes of nonlinear curves that we try to straighten up. So just so you can see what I mean by this. In a grand scheme of things, what we're trying to do with each of these sets of dots that you can hear was that we would much rather make our dots as close to this straight line as humanly possible. That is what our aim is. So to do that, we need to go and do something to either, and only one of, not both, one of the scales, either the explanatory variable or the response variable. So if you can imagine that first one, that top left one here, it's kind of looking like this hanky at the moment. It's sort of been bent this way. What we want to do is basically stretch it out, stretch out one of the sides to be able to make it more like a straight line. So what we need to do probably is to go and take our x values, that would be a good start, and make them a little bit bigger, because if we make them a little bit bigger, we can stretch it out like this. Or we might want to make the y values a little bit larger so that we can make them more like a straight line. We have some different options that we can use at this point. For this first one here, we can either do a y squared transformation, we can do a log x transformation, or we can do the reciprocal of x transformation. A y squared transformation, if I use my hanky analogy here again, y squared is just making, what it's doing is squaring all the response variables. So all this clump of response variables down at this end, what they'll do is they'll push up, like so. If I've got the logarithmic of x, what it's doing is it's actually going to spread out all of the values, so it's going to look something like this. And if I've got 1 over x, what it's doing is it's actually going to make all of the bigger numbers smaller. So what it's actually going to do, if you can imagine, it's going to tilt this back up like so. What a reciprocal value does is it takes all the big numbers and puts them in the denominator, or takes all the numbers and puts them in the denominator. And what you got, so let's just say you had 10, 100, and 1,000. A reciprocal transformation is going to go and make it like 1/10, 100th, and 1,000th. In other words, 0.1, 0.01, and 0.001. And what it's doing is it's actually just shrinking it so it's all within one particular set of values between 0 and 1, rather than being hugely spread out. So it's sort of crushing them all together. In the other end, we've got this particular set of transformations on the right here. So we've got this top right curve here. We can either do a y squared transformation like we did before, or even an x squared. Because what the x squared transformation will do, so if you can imagine that's what that curve looks like, x squared makes the explanatory variables bigger, so it's going to stretch it out like this. Similarly down here, we've got the bottom curve here that we want to get closer to this straight line. And so we can either use anything really. We can either do reciprocal transformations or logarithmic transformations. And the one on the right here, we can either do a log y, 1 over y, and x squared. So what does it all mean? I've talked about transformations, I've talked about adjusting scales and things like that, but what does it look like in practice? Well, in the next few examples, what we're going to be doing is we're going to look at transformations for an example of nonlinear data that fits in each of these categories. And what we're going to do with that is that we're going to go and see this example. We're going to see what it does. And because I'm going to do an example from each one, what we're going to see is which one is the best transformation. Now, for the scope of further mathematics, you're rarely asked to do this. You're rarely asked to pick a transformation of your choice. However, in the practical real sense, this is something that you would have to do. If you actually were trying to transform nonlinear data, you'd have to go and find or use the best one. And in the next video, what we're going to do is see how you can use any of the transformations and therefore pick out the best one.